Fisher versus Neyman-Pearson. Differences in testing. Fisher's and Neyman-Pearson's data testing theories have many similarities, so much so that even Fisher himself put their differences down to just philosophical considerations. Yet, these philosophical considerations have practical ones, such as how each theory tests data and what can be concluded thereof. Let's start with actual research data already located in the appropriate frequency distribution, for example a t-distribution with 64 degrees of freedom, and with their corresponding theoretical probability known, that is, a p-value of 0.009. How do Fisher's and Neyman-Pearson's approaches, and as a marginal note NHST, differ? On first impression, Fisher's and Neyman-Pearson's tests do the same. They use a hypothesis centered on zero and with a standard error derived from the sample. They provide a convenient cutoff point for assessing the probability of the data under the hypothesis and conclude whether to reject the hypothesis under test based on where the data sit around that cutoff point. One obvious difference is that Fisher's conventional level of significance, for example 5%, is both flexible, 4–6% convey about the same degrees of evidence, and gradable. For example, we take 5% as significant and 1% as highly significant. That is, the smaller the probability you get, the greater the evidence. In contrast, Neyman-Pearson's conventional decision level, for example at the 1% alpha level, is fixed. That is, 1% and 0.9% convey different meanings. It is also non-gradable. The question now is, well, apart from all these obvious differences, are there other testing differences to pay attention to? Fisher's test sets up a theoretical null hypothesis in order to provide a sampling space for the research data. It is just T1 hypothesis, and thus any research data can be located in the distribution. The test observes how extreme that is improbable. The research result is under this null hypothesis, and so the research data become evidence against the null hypothesis. The actual test is based on a rational assessment. Is the research data so improbable under the null hypothesis that we may doubt this null hypothesis explains the results? The p-value is quite informative in this context, which is why it is the preferred source of evidence. Conventional levels of significance, for example 5 or 1%, may help in making such assessment, and being flexible and gradable allows for a better ascertaining of the evidence. Yet, there is only the null hypothesis, so the research result is still possible under this null hypothesis despite any evidence. That is, there is no alternative hypothesis. What passes for the alternative hypothesis is actually the negation of the null hypothesis, which contributes nothing to the test. A Neyman-Pearson test does have an alternative hypothesis, and here is where lies the main difference. Important consequences of this are that the test becomes a decision between competing hypotheses, and controlling decision errors in the long run becomes important. Meanwhile, the evidence of the data in the individual research is of little relevance, and for example a critical value is preferred to a p-value. Now the alternative hypothesis provides information about the effect size in the population, about the type 2 error, and about the power of the test. An alpha is not a level of significance anymore, it is an error probability. The cutoff therefore needs to be fixed because it is a decision threshold between the main hypothesis and the alternative hypothesis, given the alpha and beta error probabilities. Now, going deeper, we could actually consider a Neyman-Pearson's test as a Fisher's test of significance carried out at a particular time and with a particular sample, where the main hypothesis is the null hypothesis and the alpha level doubles at the local significance level. Underlying such significance test, however, is a definite population that provides a specific alternative hypothesis, a measurable effect size, a decision strategy based on repeated sampling, and the opportunity to control decision risk in the long run. Therefore, you could consider a Neyman-Pearson's test as a reduction of a research question at population level to a test of significance at sample level. And this brings about an interesting realization. Unless the information provided by this alternative hypothesis is taken into account, the test simply defaults to a Fisher's test of significance. Following the same logic, we could also have a deeper look at Fisher's test and see it as wanting to be a test of acceptance, that is, wanting to test an unknown and thus uncontrolled alternative hypothesis, which, by the way, is the hypothesis of real interest and the one that motivates the research in the first place. Thus, a Fisher test can be considered a Neyman-Pearson's test, but with a known population effect size, uncontrolled type 2 error, uncontrolled power, and Robin alpha, all subject to a posteriori assessment. In a way, a test of significance is like a test of acceptance that thought it could. As per the interpretation of a research result, when using Fisher's approach, the result ought to be interpreted as evidence against the null hypothesis, based on the probability of such a result occurring under such hypothesis. The interpretation is a dual one, either an unlikely result that happens about 9 times in 1,000 just happened, or the null hypothesis does not explain the research results. Under Neyman-Pearson's approach, however, we ought to conclude that the alternative hypothesis explains the research result better than the main hypothesis does. Notice here that the alternative hypothesis is not that the results are greater than 0, thus that there is a difference, but that the difference is specified as the effect size in the population, that is, for example, a large effect size, is the one that explains the results. The actual effect size found in the sample is of little relevance. So, at the end, aren't both conclusions the same, you may ask? The best reply is to base the answer on a post-hoc analysis and observe what we can learn about the population. Fisher's test would estimate the effect size to be 0.61 and have power of 0.50, while Neyman-Pearson's test knows that the effect size is 0.80 and has power of 0.80 as well. Thus, in our example, Fisher's test both underestimated the effect size and was rather lucky to reach a conclusion similar to Neyman-Pearson's. So, the main message to gain from here is that the alternative hypothesis makes all the difference between those two approaches, between Fisher's and Neyman-Pearson's test. What about NHST, you may ask as well? Well, what about it? NHST works mostly like a test of significance, attempting to achieve a decision between hypotheses. However, NHST does so with some important shortcoming. It doesn't care about the alternative hypothesis, actually it takes the negation of the null hypothesis for the alternative hypothesis. It doesn't care much about beta and power either, and it uses P both as evidence against or in favor of the null hypothesis and as a long-run type 1 error or Robin alpha. It also aims to prove or disprove hypotheses. Therefore, NHST will end up getting similar results. Remember, it defaults to a test of significance technically, but will conclude the following. The null hypothesis is rejected with a probability of about 1%. The alternative hypothesis is accepted with a probability of 99%. The probability of being wrong in reaching such conclusion is also about 1%, and a replication will achieve similar results about 99% of the time. This is a lot of nonsense, in case you were wondering. And the best policy is to ditch NHST in favor of either Fisher's or Neyman-Pearson's approach. If you want to know more, there are some references here, and with this we finish this presentation.